Good afternoon, everyone. Thanks for coming to this virtual presentation. Again, my name is Shahrokh Valaee. I'm from the Department of Electrical and Computer Engineering at the University of Toronto. And before talking about the topic of the research that's going to be discussed today, let me introduce my lab. I'm the director of Wireless Internet Research Laboratory. I started this lab and I joined U of T about 18, 19 years ago. There have been a lot of people that have passed through this lab. We have had professors on sabbatical, visiting researchers from different companies, postdocs, PhD students, master visiting students, undergraduate students. And I have to give them credit. Our research will not be doable without the contribution of these people. So whatever I'm talking about today, I have to share the credit with everybody else who is in my lab. In the lab, we work on different clusters of research on machine learning for medical imaging. That is going to be the main focus of today's talk. We are also actively working on research in 5G, 6G cellular systems. This is for mobile communication. In localization of Wi-Fi and LTE terminals indoors where there is no GPS. And for vehicular communications, this is vehicle-to-vehicle communication, which is for next generation cars, autonomous cars, that will be equipped with these communication devices that they can talk among themselves and they can talk to internet and infrastructure. Okay, the research that I'm going to be discussing today is collaboration with one of the hospitals that we are working on. We are collaborating. We are collaborating with two hospitals, St. Michael Hospital and Toronto General Hospital. In St. Michael Hospital, we are working with Department of Radiology. And in Toronto General Hospital, we are working with the Department of Internal Medicine. So our collaboration is creates a very nice environment by them giving us clinical problems and data. And from our end, we produce models, suggest models, and machine learning methodologies. We implement them, we test them, and we send them back to our peers in hospitals to evaluate. And this feedback actually goes on, and we correct our models, and we send to our peers. So it's a win-win situation in this case. Okay, so let's now get into the talk of today's focus. So I'm putting here an image. This is an X-ray, chest X-ray of a person. Okay, and I would ask you, what is wrong with this image? Okay, if you're not a trained radiologist, you would say, I don't know. For me also, it didn't make sense at the beginning when I saw this image. Let me share you another image. Okay, so you move it to the side, and there's another image. And I tell you, this is normal. The one in the right-hand side is a normal image. The left-hand side is not normal. Okay, you might say there's something here which is bigger here. And you're right. So there's an organ here which is enlarged in the left image compared to the one that is normal. So this is the organ. And that's the heart. So this patient has enlarged heart, cardiomegaly. Okay? So by looking into this and comparing these two images, we were able to find out what was wrong with this image. So let me give you some more examples. Okay, I'm trying to train you as a cardiologist, as a radiologist. Okay, here we have a cardiomegaly again. Same thing here. 2 images, enlarged hearts, as you can see. As my laser pointer is moving, you can see. On the right-hand side, 2 images. Hearts are small. Okay, it's a heart small here, small here. So we were able to differentiate between these 2 types, normal and cardiomegaly. So these are the hearts. Let's go to this page. I pause for a second, and I want you to find the cardiomegaly case here. I have 4 images, and 3 of them are normal. 1 of them is abnormal. And the abnormality is enlarged heart. Okay, so here I see this heart. This is the heart. This is the heart. And this is the heart. Okay, and you can see that my laser moves more here. So this is the enlarged heart. So we were able to identify this enlarged heart. So congratulations, we just trained your eyes. Okay, so back to that training images. I showed you these 4 images. I didn't tell you anything about them except that the left 2 images, they were enlarged hearts, and the right 2 images, they were normal. But there was one piece of information that I hid, and that's here. The very left image, it's a real image. The second from the left, it's synthesized image. It's not a real image. There is no person with that image or with that X-ray. Again, this is a real image or real X-ray. This is a synthesized X-ray. There is no person with that X-ray. Okay, so we train your eyes with mix of real, true images that were taken from patients, and with synthesized images, images that they were made by computers. These are not real people. These are computer-made images. Okay, so how is it useful? We will get to that shortly. Let me see how we can do that. How did our brain analyze and find out? So I'm not a doctor, but in this one page, I'm trying to just review quickly how brain works. In brain, we have neurons, nerve cells, in billions, 80 billion to 100 billion neurons. They have 3 parts, soma, axon, and dendrites. And each neuron is connected to neighboring neurons, to other neurons, maybe to 1,000 more other neurons. Okay. Each neuron is charged negatively with negative 70 millivolts. Okay. If the charge of the neuron goes higher, it reaches to negative 55 millivolt, then it fires. It sends an electric signal. This electric signal moves along these axon, where my pointer is showing, turns into a chemical signal, and then can be observed with the next neuron. So these neurons, they can communicate together by sending information. So information went from first neuron to second neuron. And how it worked? By firing, by activation of the first neuron and transmission of the information to the second neuron. Okay, so back to our problem. How can we generate those images or use machines to diagnose the images? Okay. Okay, we'll get there, but first let's see, can we make or can we build a neuron? A machine, basically. A small machine as a neuron. Okay, here I have a neuron. It's symbolically represented by a, say, circle. And there are some connections that are coming from the previous neurons. So I have X1 is another neuron, X2 another neuron, and Xn is another neuron. So each neuron is connected to n previous neurons. Okay, if X1 fires, then that information passes to my neuron by maybe multiplication by some weight W1. Same thing for neuron 2 or X2. If X2 fires, that information passes through to this neuron by multiplication by W2 and so on. So at the neuron, I have input X1 to Xn multiplied by W1 to Wn. So I'm writing this as the sum. So I'm multiplying the voltage value of the previous neuron times some weight and adding them all together. Plus some bias, which is local to this neuron. I have now an input to this neuron, which is the bias plus the multiplication of my weights with previous values or values of the previous neurons. Now, this is the input. The output is a curve. Okay, so this curve, you might be able to define or design different curves. But in the simple form, this can be like a step function. For example, for all z less than 0, I can have a value which is less than 0.5 here. And for all z more than or positive values, I can have a value which is more than 0.5. So this can be similar to firing in each neuron. So by way of this composition, we were able to build a synthetic neuron, which is one of the small elements in our neuron or neural network. Okay, so let's add a number of those neurons together. So I have a network of these neurons. So each circle that you can see is one neuron, which is connected to previous neurons and to subsequent or next neurons. In this figure, I have 1, 2, 3, 4, 5 layers of neurons. The first layer is called input layer of the neurons that they do the sensory from outside. The output layer is the result of our decision. And there are some hidden layers that I have here, 3 hidden layers that they are basically the bulk of the brain of this neural net. Okay, so how this neural net I would like to work is that I want this neural net to identify 4 types of images: ship, dog, cat, and automobile. Okay, so if I put a ship, I want the output ship to be 1 and the rest 0. If I put a dog here, I want the dog to be 1 and the rest 0 and so on. So how do I make that happen? By training this network. The same way that we trained our brain or our eyes when we were looking to those cardiomegaly images. Okay, so I have a network. I introduce a large number of images of, say, dogs. Okay, I have here 6 different images. This should be in hundreds of thousands and over or maybe even millions of images. So I introduce those images, I put those images to this input. Each input element is one of those pixels. So if, for example, this image is 512 by 512, you have about 25,000 neurons at the input. They are connected, and the output, I want this, this pin or this output to be 1, the rest 0. Okay, so I put one of these images at the input. I force this one to be output, or I want, not force, I want this to be output. I look into what output the network is giving me. I find the difference between my desired output, which is 0, 1, 0, 0, with what output my network is giving. Okay, I find this difference, and then I go and adjust these weights. As I adjust these weights so that the output becomes similar or close to my desired output. I change the image, put a second image, do the same thing, third image, fourth image, and all those hundreds of thousands of images, I pass through those. Each time I adjust these weights a little bit, a tiny bit. If I do this, I can train this network, and network would be able to identify a dog if I give the network a new image, which is not among these training images. It's a completely new image. It would be able to identify the dog. Okay, so how do we use that in our network? Fine, so we could do that for dog and cat, but what about our pathologies? So here on the left-hand side, we have a number of cases, 5 or 6 different cases with different types of X-rays. The same way, I have a network here. It's a bit more complicated than the network that we saw in the previous slide. Nevertheless, it's a neural net. We put images, and with a label. That label says what type of image this one is. For example, this is a normal one, or cardiomegaly, or edema, or whatever. And then we change these weights so that the output gives us the desired output. Okay. In practice, we have to shuffle them. We cannot just introduce one type. You have to randomly put one image of all these different types, and then adjust the weights appropriately. Okay, so I want to do this. Let's go and see a practical case. This is the data that we got from the hospital. Okay, I have 3 types of data. I will go through them slowly. We have 5 different classes: cardiomegaly, normal, effusion, edema, and pneumothorax. Blue bar tells me how many samples do I have. Samples means images. So from cardiomegaly, I have 15,098 X-ray images. Normal case, I have 13,000, effusion 12,000, and finally pneumothorax 2013. So you can see that there is an unbalance of data. Some anomalies like cardiomegaly is more common, and some are rare like pneumothorax. Okay, good. So I have an unbalanced data set to start with. This is, I want to use this data set to train my network, but it's unbalanced at the level that you can see. Okay, I can use all these blue bars, all data that I have, to train a network. Okay, so I have here, I have my option. One option is to use all available data, all this blue data. Another version or another type is let's equalize the number. What happens if I use all blue ones is that I'm biasing my network towards cardiomegaly. So it works fine for cardiomegaly case, but it doesn't work as well for pneumothorax because there are not enough samples of pneumothorax to train the network properly. Okay, to equalize the system, I can do this. I can take 2013 samples from pneumothorax and the same number from all others. Pneumothorax was the smallest number, 2013. So I just equalize the numbers across all classes. So I have now 5 classes with 2013 samples each. So I can use them to train the network, and I show them by this green option or second method. The third method is to synthesize data, to generate data. All these orange bars that you can see here, these are all synthesized data. So for cardiomegaly, I created 15,000 samples. For normal, I created 16,000, and so on. For pneumothorax, we created 28,000. So that altogether, there are about 30,000 samples. So I have now equalized the number to 30,000 samples, but they're half or partly real and partly synthesized. And in some cases, you can see that most of them are synthesized. For edema and pneumothorax, you see that most of the data is synthesized. Okay, how do we synthesize data? Okay, so talking generative adversarial networks, or GAN, is a methodology to create data. Okay. How GAN works is you have a random input, so it's a random number on the left-hand side, random number. You have a generative network that creates another random number. So in the left-hand side, I have a distribution which is uniform. In the right-hand side, I have a distribution which is not uniform. This is similar to what we do when we want to use our computer to generate, say, a Gaussian distribution or a Poisson distribution. So we generate a uniform, and then we do some transformation so that make it into a different random distribution. Okay, my desired distribution is shown by blue, and this is, say, those real images, and this is my synthesized images. You can see that some of the images, they are mixed together. We cannot separate them easily, and some are very separate from each other. So on the top here, right, images that have been generated, or these random numbers that have been generated, is very different from the true one. GAN, it's called Generative Adversarial Network. It has 2 networks. So we have a generative network similar to what we had in the previous slide, and we have also a discriminative network. So the role of this discriminative network is to say that image that comes in is a real image or synthesized image. Okay, and we train these 2 together. They play a game. Generative network adjusts its weight so that it fools the discriminative network, so that it cannot identify a synthesized image from a real image. On the other hand, discriminative network tries to differentiate them as much as possible, to force them to look different, or to identify, classify them as true or synthesized image. They go into a game, and we, by introducing images and random numbers and training them, we are able to train them together. I don't go to the details because I don't think that we will have time to do that. But let me show you some images. Try to guess these celebrities. Have you seen them anywhere on TV or on camera somewhere? I'm sure you have not, because these are not real images. These are not real people. These are all synthesized images. And they have been generated by GAN. Okay, and I have shown the where you can find the references to those images. Okay, so how do we use GAN for our purpose? We have generator network on top and discriminator network. So random number at the input, the random number goes through this generator network, creates an image. Okay, this image comes out as an X-ray or candidate X-ray. We mix randomly with these images with real images. And then we pick randomly from one of these two data sets or pools and give it to a discriminator. Discriminator is supposed to say this is a real image or synthetic image. So makes a decision based on real, synthetic. Based on that decision, we go and adjust the parameters of these two images. And we keep going with this until we reach to a point that discriminator cannot discriminate, or otherwise said, the error in this discrimination becomes about 50%. So it's like a flipping a coin. Discriminator cannot say whether this is a real image or this is a synthesized image. At that point, the game is over. We take this generator now. This generator has been now trained and can generate a number of images for us. Okay, so we do this. We put random numbers here. We use that trained generator now to create images. We mix those images with real images. So for example, if this was pneumothorax case, I had about 2,000 of real images and 28,000 of these generated images or synthesized images. We randomly pick from them and put into another network. This is a new network. This is the blue network, is a classifier. This classifier is expected to identify the different classes for us now. So it's cardiomegaly, pneumothorax, edema, effusion, normal, or what. So here I have image of all 5 different categories, real and synthesized, randomly mixed together and pushed into this classifier. And this classifier would be able to, we will be able to train this using the pool of real and synthesized images. Okay. Then this classifier, this new design classifier or the trained classifier, can be used to identify real cases this time. So let me first show you a graph of generating images. On the left-hand side, you see the data is generated. So the different, I have, I think, 8 by 8, 64 different images are created. These are the real images. These are the synthesized images. When we show these synthesized images to our radiologists, they say, okay, well, I can see that the quality is not good, but I can identify the enlarged heart, for example, here. I can find out that the heart is large. So these arrows that you can see here, these are put by the radiologists. Okay, so let's try these 3 types of data for training our classifier or our final classifier. Real unbalanced data set, call it DS1. So these are all those blue bars. The actual number of X-rays that we got from the hospital. DS2 refers to the system that uses real and synthesized data set combined together, meaning these orange bars and blue bars together. And finally, DS3 is green bars, which is the equalized or balanced number of data points or images. Okay, we trained two networks, two classification networks, AlexNet and GoogleNet, with all these three sets of data. For each one, we used all these three separately, and then we looked into accuracy that we could get. Okay, again, DS1 is real balanced data, and the accuracy on total that you get is about 70%. For example, for AlexNet. For DS2, which is real plus synthesized data, you get to 92% accuracy. And when you use just balanced data with 2,000 samples, because the number is too small, you get about 58%. The same thing happens for GoogleNet. You can see 93%, 71, and versus 59. Now, if we look into the individuals, for example, cardiomegaly versus pneumothorax. Remember that this had, cardiomegaly had a large number of data points, and pneumothorax had smallest number. Cardiomegaly was about 80% with 15,000 samples. Pneumothorax was about 57% or 58%. From 79%, it moved to 95%. And pneumothorax from 58% moved to 88%. So this is like 30 points more, and this is about like 15 points or 16 points more. So your accuracy is quite significantly higher in those cases that are rare cases. And these are the ones that are usually missed in hospitals. It's much easier to find or to diagnose cardiomegaly versus pneumothorax or edema because the number of cases are small and these are rare cases. You can see also the trend when the number of iterations changes. You can see that significant distinction or separation happens when we are using the synthesized data along with the real data. Okay, one other aspect of this work, which is, I think is important, is that the issue of the privacy. Hospitals are usually bound by privacy code. So you cannot easily move the data from hospital to outside or to even to other hospitals. It has to be sanitized in the sense that you have to remove all information that pertains to the patient. And even after doing that, it's still difficult to move the data outside. So for that reason, usually they want to house the data on their servers, and they don't want to share it outside. Even for us, my students, they have to go and sit in the hospital to do their research there. But this synthesized data is not bound by that, because there is no person that has that X-ray. So it's easily portable. You can easily create it in your lab and send it to any place that you want. And you can also balance the data as we saw. We can create more samples from rare cases that you cannot easily find them in the hospitals. And we can also see other examples of that in the next slide. Let me show you one other application of this GAN before we end this talk. When you go to screening in airports, most of the cases, 99.99% of the cases, are clean or clear cases. So you don't carry guns or anything in your wallet or your briefcase. So if you train a machine, if you want to train a machine to identify those components that you're not, or articles that you're not allowed to bring to the airplane, for example, knives or guns or etc., you don't have enough samples of that. There's not enough real samples of that. So you can generate images that these are synthesized images of guns, knives, and other sharp elements, and then you can train a machine to do that. This is just one other application of that. So let's summarize. We talked about machine learning and how it can help physicians to diagnose diseases better. It cannot replace them, at least not yet. There's some discussion on whether or not this machine can replace a physician. The neural networks are a class that they use machine learning, and they can accurately surpass, actually, in some examples, the accuracy that you can get by human being. We have many examples of such. Deep neural network are a subclass of neural networks that they are the ones that we are basically talking about. These are the, when we're talking about deep neural network, we mean that there's many layers of hidden layers inside the network. Generative adversarial networks can generate and can synthesize data so that it can subsidize for the places that there is absence of data. And if we use this synthesized data for training networks, we can get very high classification accuracy. So that's end of my presentation, and I'll be happy to take questions. Okay, so I will read the questions and then I'll try to answer. Currently, is the relatively low image resolution of MRI scans and ultrasound a limiting factor in the application and impact of machine learning technologies for medical imaging? Thank you very much. It's from Kevin from Beijing. Thank you very much for the question. For some application, yes. If, for example, you want to do segmentation, yes, you need high resolution or better resolution scans. But for some applications, our MRI applications, or actually X-ray applications, we didn't have that problem, because the organs that we were looking for and the classes that we were looking for, they were relatively distinct, and they were, as I said, doctors, when they looked into the images, they said, I see it's a noisy image, but this, I can say that this is like a bad machine took the image. So but I can still diagnose it. So it was even though our images, they were not perfect, we could use that for our application. Another question from Halifax, Canada, Edward. Over 2 million people infected with COVID-19. How many are needed for an adequate data set for ML? And that's also a very good question. So true, a million people, they're infected with disease. My brother actually is a doctor, and he says that as soon as I see the scan of the image, I don't wait for the diagnosis, for the lab tests, just to start the treatment. So true, we have 2 million people infected, but do we have their data gathered, cleaned, labeled, and located in a place that we can use it? We don't have at that point. Sure, certainly at some point, hopefully, it would be possible to do that. But as I said, COVID-19 is so clear that it doesn't really need much of machine intelligence to dig out the rare cases. It's easy to find from the from X-rays, even for MRI, or CT. Or CT of the chest actually shows it vividly and completely clearly. This is from Shashwat Sharma. In the pneumothorax case, the issue was insufficient training data. Isn't that still an issue now for GAN rather than the final classifier? In other words, it seems that the issue of insufficient training data has been transferred from one network to another. Is that a concern? Okay, so yes, there is insufficient data, but if I go back to slides, okay, here, the random number generator that we are putting here, it can change. So I can change this random number as randomly and pick new random number. So by this way, I can create many more data, as many as I wish. So that's why we are saying that it is a small number. The real cases are small, but we augment that by randomly generating images that they have that pathology in them. Okay, as I said, the quality may not be as good, but the pathology is vivid and clear in those images. So from one sample of real image with multiple running of that latent random variables, we can generate multiple new images. So we can augment that way. These are all going fast. How can we incorporate other data with images in the AI analysis, i.e., what about other medical information along with images? It's a very good question, Peyman Shokrulahi. Yes, you can do that. We are actually doing it for another case for lung transplant patients. So you can have a multimodal diagnosis. You don't need to just have X-ray. You can add the age of the patient, for example, their body size, their gender, etc. So you can augment the diagnosis. Can happen. It's a multifaceted. That's absolutely true, and that's the way that the doctor does that. And that's why we are saying that right now at this stage we are not replacing doctor with machine. This machine is just helping. It's like it's a helper to sift through and find the cases that they need a closer attention from the doctor. I give you one example that I was reading recently. Google made they're doing some tests for diabetic patients in Thailand. So if you have diabetes, you might end up with retinopathy in the eyes. So right now, when a nurse takes an image from the eye, it goes to a machine and it diagnoses whether this is clean or it needs further attention. So systems of this type can be used in that setting, that you can sift through, find cases that they need closer attention, and then send it to the doctor. Can one synthesize data attributes, column values instead of data set rows? I'm not quite sure I understand this completely. Okay, I mean, okay. So like new pathologies. I haven't seen that you can create like celebrities as we showed there. New person, that's a new person. So it's like basically moving along that line. But creating new pathologies that they don't exist, I haven't seen any. You might be able to combine pathologies. Might be able to say, okay, a person that has both pneumothorax and cardiomegaly. You might be able to do that. We haven't done that, but that's a very good question from David. Thank you. Has this type of application been used in the current climate to diagnose COVID-19 cases? This is from Nick. If so, how does the technology assist to differentiate COVID-19 symptoms from other lung diseases such as pneumonia? No, unfortunately, we haven't. As I said at the beginning, we don't have access to that cases. We haven't had like we haven't seen images of COVID-19. We have not been given, so we don't have enough samples to test that. But certainly, that's a good plan moving forward. I have 3 questions. This is from Navid. Can we use other methods to generate data? For example, SMOTE and ADSYN. That was yes. Are there cons and pros in comparison to GAN? Yes, you can do that. Absolutely. We have done that. We didn't. I didn't propose show it here. We did it for other images, for MNIST images like handwriting, and by moving, rotating, shifting, flipping, etc. GAN actually still works better compared to those ones. So we have comparison in our papers for other types of data generation. And also how many images at least we need to train a GAN network. Okay, so unfortunately I don't have the number in my head. It is, I can maybe draw from this image. Here, we can see about 100 iterations of our algorithm. But how many images, I don't know. This is something that I can, well, my students, they know much better when they do the, than they do the simulations. So in terms of the actual numbers, I have, unfortunately, I don't know how many images need to, this is actually for classifier, for doing the classifier, but how many images to do the train the GAN, I don't, or how many iterations to do the GAN, I don't know, unfortunately. And 3, do you use a pre-trained AlexNet or GoogleNet? At this, no, these are from scratch, but that's possible to do. Yes, you can do pre-trained ones, but this is some information that, some data that we got a couple of years ago. So no, we didn't we use at the time. These are from training from scratch. What is the role of the radiologist or other image readers in this process? Jim Courtney is asking. As I said, the final call is on radiologist. This is just assistant. Here, it just makes an assessment. Especially this assessment is very useful when we were talking to our colleagues, radiologists. They said that like pneumothorax or edema, they can be easily missed by like residents, that they're not completely fully trained and their eyes are they're still in the learning process. They might miss those cases. A machine like this can say, I can see pneumothorax. Do you see that? So it basically, it's a feedback mechanism to radiologists. So radiologist makes the final call, and this is an assistant, basically. To address the imbalanced data set, can resampling techniques be used? Also, by generating new data points using GAN, will the final classifier learn the weights generated by GAN rather than the weights of the true samples? Thank you. simming. Resampling, yes, can be used, absolutely. Actually, we have another work. Again, I didn't discuss it here. We do polar sampling of images. In some cases, we have seen, especially that's very useful for segmentation, and it can be can be a very useful method to increase the accuracy. But again, I don't have the data here. For some application, we could use that, not for all. And this is still ongoing research, and so my student is working on that. I don't have a solid answer to say that definitely it helps in all cases, but in some cases, yes, it's absolutely useful. Let me see, it just popped up. Why particularly AlexNet and GoogleNet for transfer learning? Okay, this is there's no reason, actually. There's no reason. This was as I said, these are the first networks that we designed when we were talking about GAN. After that, we looked into other networks and similar improvements we could see in ResNet and I think it's Inception, and so no reason. These are the first samples that we have. No particular reason why we chose these two. Do you know about any free medical data sources? There is a lot of data sources for different applications, for different, it's been generated in at different places. Stanford, I know a few, MIT. We're working on some database that we might release it, and but yeah, it just by Googling you can find it. We have used, like for example, one of the that we're now using is for fracture finding in the neck and spine fracture, and so you can easily see by Googling. What's the minimum number of sample data required for using GAN models with regard to the ones available in less quantity, like 2K? Okay, that is from Rajshri. That how many can I reduce it to 0? This is something that we are currently working on. The images that we had at the beginning, they were made by DC GAN, which was the simplest form of GAN. We are now going to style GAN and other methods of GAN, and images that are becoming sharper and better. What we want to do, and we have not done yet, is to reduce it to 0. So can I completely train a network with synthesized data? In the beginning, we were not successful. So again, I don't have in mind, like, was it 500 or 1,000, or what was the small number of the real data that we wanted we needed to mix with the synthesized method. But as you mix more and more real data, it starts to grow. We didn't see any sharp transition that would say, okay, there's a threshold effect that below this it crashes and after that it improves. We saw gradual move, but what we wanted to do is that we wanted to reduce it to 0 and see what happens. At 0, it couldn't work, but it was increasing. That accuracy was increasing as we introduced more and more real data points. Does DICOM protocol have a role in your work? I think that's for. We didn't use that. No, we didn't. But I think it relates to the previous question, that can we add other modalities to that? Yes, yes, it can. We are still experimenting with that. The fact that this is like a specific protocol of DICOM in medical imaging. No, we didn't use that in our studies. Are the validations or test real images used? No, these are absolutely real images. After after GAN is completely trained, we use GAN to generate synthesized network, the data. Synthesized data plus real data are used to train a classifier, and the classifier just uses real data after. For validation, for testing, we just use real data and no synthesized. What about modifying the GAN outputs with image operations such as rotations and mirroring? Yes, I think I answered that one. Yes, we did that, and the improvement was not, actually there was no improvement when we, so what we did was that using rotation and mirroring, etc., versus GAN, we didn't combine them together. Rotation of the data, GAN, and GAN worked better.
Professor Valaee, I'm gonna jump in
Okay.
as we've reached our time. We've been a little bit over time because of the technical issue that we had. But if you are willing, we will share your email address with people if they have any burning questions that we will share along with the slides that will follow up with everyone if they'd like to reach you. Would you be okay with that?
Absolutely, absolutely. Thank you very much. Yes, slides. I have sent a copy of the slides and it's available.
Absolutely, that's wonderful.
Yes, I'm not sure that it's on my slides, but was it in my slides? My email address?
It may have been at the end.
Okay.
I just want to say a big thank you to Professor Valaee, and thank you for your grace during that period as well. I clearly need to come up with a list of filler jokes for times when technical issues happen. We truly appreciated your insights today, and thank you for joining us, especially during this difficult time. I know we had to reschedule because you were also trying to accommodate your teaching schedule and going online with all your students. Thank you for making our engineering community, our students, our alumni, a priority. I want to thank all the viewers for your patience and for your thoughtful questions. I hope you learned lots today. For those of you who are new to the School Lunch and Learn, we host events typically on the second Wednesday of each month between October and May. Our next Lunch and Learn is scheduled for Wednesday, May 13th, and will be hosted exclusively online once again. We hope you'll join us for a presentation with Joseph Orozco, who's the Executive Director of the Entrepreneurship Hatchery here at U of T Engineering. That session will be called The Development of the Entrepreneurial Human Capital. If you haven't had the chance to sign up again, our next alumni event is actually next week. It's our alumni edition of Coffee with Chris. This is with Dean Chris Yip. He holds a weekly Coffee with Chris with the students, and we thought it would be great to actually have a Coffee with Chris on May the 6th with alumni. You'll be able to have a virtual coffee with him and he'll be able to answer questions and give you updates on engineering's activities and how the faculty rose to the challenges during this period of the COVID-19 virus. Both of these events are of course free and open to all engineering alumni. We hope you'll be able to join us for these and more online events to come in the future. Details on how to register will be sent out to everyone in the days following this event today. And with that, on behalf of the Alumni Office and the Faculty of Applied Science and Engineering, I hereby adjourn today's meeting of the School Lunch and Learn. Whether you're near or far, we're so thankful you were able to join us, and we wish you a safe and happy day. All the best.
Thank you very much for inviting me. Also, I enjoyed being today in the virtual. I hope that at some point you can shake hands with all alumni in person.
I 100% agree. I couldn't agree more. Thank you so much, Shahrokh. It was a pleasure to have you, and thank you to all our alumni out there. Be
Thank you
well,
very
everyone.
much for
Take
having me.
care. Bye-bye.
Bye bye now.